Chapter number 9, Plane Monochromatic Electromagnetic Wave. In this chapter, we are going to derive the Poynting theorem and we will state the theorem. We are going to define the Poynting vector. Chapter also shows how the Newton's third law will act in electrodynamics. We will find the velocity of light finally under the heading of the plane monochromatic wave, electromagnetic wave. We will derive the equation for electric field and magnetic field vectors for the waves and their behavior. In the chapter discussed about the energy, momentum and Poynting vectors of electromagnetic waves in vacuum. Continuity equation for the Maxwell equation. We already have discussed the continuity equation, but at that time the Maxwell equation has been not right. Now we will see under the umbrella of the Maxwell equation how the continuity equation will derive. Ampere's law with the Maxwell correction and modification is shown in the below. Del cross B is equal to mu naught J plus epsilon naught divided by T of E. Now let's try to find del dot del cross B. Now therefore del dot del cross B is equal to del dot mu naught J plus mu naught epsilon naught divided by T of E. As you know, divergence of a curl is always 0. Therefore the left hand side of the equation becomes 0. But about the right hand side, we know del dot E by the Gauss law is rho by epsilon naught. If we substitute that value over here, we will get 0 is equal to mu naught del dot J plus mu naught epsilon naught 1 upon epsilon naught divided by T of rho. Now epsilon naught get cancelled, and if you take mu naught as a common term which is equal to 0, then we will have del dot J is equal to minus of divided by T of rho. This is the equation of the continuity, and here we have drawn the same equation of continuity from the Maxwell equation. That shows that the Maxwell equations follows the principle of the conservation of the charges. Poynting theorem. Work done related to accumulate a static charge distribution is given by in electrostatic W work done is equal to epsilon naught by 2 integration E square d tau. Similarly, the work required to current flow in magnetostatic will be Wm is equal to 1 upon 2 mu naught integration B square d tau. This makes if we add this work done, we will get total energy stored into the electromagnetic field, which is E equal to half integration epsilon naught E square plus 1 upon mu naught B square d tau. According to the Lorentz force, F is equal to Q E plus V cross B. Therefore, work done on a charge in an interval dt is the force on the charge up to the length of dl. The dw is equal to F times dl. Now F is the Lorentz force, that is F equal to Q times of E plus V cross B. And dl is the length segment, which is nothing but velocity into time, that is V into dt. Now, as you can see, V cross B is equal to 0. Since we know that divergence of a curl is always 0. This term, second term, it's not a divergence, it's a dot product and cross product. These terms get 0. What remains? Q vector E velocity V dt. Now, if we take this dt to the left hand side, so dw divided by dt is equal to QEV. And since we know that Q is nothing but rho d tau, we will substitute the value of rho d tau in place of Q. Therefore, dW divided by dt, that is derivative of work done with respect to time, is equal to electric field E vector into the velocity rho beta. Now, if you see this velocity and rho, this is nothing but the current density J. Therefore, we got the work done as an integration over volume electric field E dot J. Now, let's suppose about this E dot J terms. This is the integration terms, and we will try to find this what will be the E dot J. And by Ampere's law, with the Maxwell correction, we have del cross B is equal to mu naught J plus mu naught epsilon naught deva by deva T of E. If we divide this mu naught toward the left, we will have del cross B by mu naught, and this term to the left minus of epsilon naught deva by deva E by T is equal to J. So we will get the value of J. Therefore, we will find the value of E dot J. Therefore, E dot J is equal to E dot del cross B by mu naught minus epsilon naught deva by deva T of E. If we open the bracket of above equation, we will get 1 upon mu naught E electric field dot product del cross B minus of E epsilon naught deva by deva T of E. Now, in this term E dot del cross B separately, in what we have already learned through the vector algebra and divergence, that del dot E cross B is equal to B dot del cross E minus E dot del cross B. Now, this is what we have, E dot del cross B and E dot del cross B. Therefore, this E dot del cross B is equal to B dot del cross E, and we will take this left hand side term del dot E cross B to the right hand side. We will have minus of del dot E cross B. Okay. Now, by Friday law, what we have learned, del cross E is equal to minus deva by deva T of B, that is partial derivative of magnetic field B. Then we can replace this del cross E by minus deva by deva B of T. Therefore, E dot del cross B is equal to minus B dot minus of deva by deva T of B minus del dot E cross B. Now, this term B dot del deva B by deva T is actually the partial derivative taken with respect to the time. It is half deva by deva T of B square. And the same equation, if you say E dot J, it has epsilon naught E dot deva by deva T of E. Therefore, this is also a partial derivative. That means E dot deva by deva T E is equal to 1 by 2 deva by deva T E square. Now, for the time being, let's substitute half deva by deva T of B square over here for E dot del cross B. Therefore, E dot del cross B is equal to minus of half deva by deva T of B square minus of del dot E cross B. Now, further we go. This equation will substitute into the E dot J in place of E dot del cross B. Therefore, E J is equal to 1 upon mu naught minus 1 by 2 deva by deva T of B square minus del dot E cross B minus of epsilon naught half of dB t of E square. Now this is also E square and this is also B square. So let's make them a group, and we will have half as a common term outside, minus as also a common term outside, minus dB t of epsilon naught E square plus 1 upon mu naught B square. And other terms remains like this, minus 1 upon mu naught del dot E cross B. Now this E dot J has been taken from the integration terms of dw by dt. If you remember here, dw by dt, E dot J. We have find E dot J as minus half of dB t of epsilon naught E square plus 1 upon epsilon naught B square minus 1 upon mu naught del dot E cross B. If we substitute that value into the derivative equation of work done with respect to time, we will have this result. Now, when the partial derivative is taken outside of integration, it becomes a full derivative. Therefore, minus d by dt integration over volume, we have divided the volume into integration and open up the bracket, half of epsilon naught E square plus 1 by mu naught B square over the volume minus 1 by mu naught integration over the volume del dot E cross B. Now, if you see this term, okay, and if you apply divergence theorem over here, you will get 1 upon mu naught integration over closed surface E cross B over the surface dA. Now, this is the Poynting theorem, and it says that the work done on the charge by the electromagnetic force is equal to, work done by the charge on the electromagnetic force is equal to decrease in the energy, this is the form of energy, decrease in the energy stored into the field and less the energy that flow throughout the surface. That means how much energy has been decreased to do the work plus, you can say, and how much energy has left the surface. That is the work done, total work done. Next, Poynting vector. Energy per unit time per unit area transported by the field, it is given out by the field, is called Poynting vector. Now this is what we have, a Poynting vector. This is the term shows that the energy is leaving the surface, going outside of the surface. S vector is 1 upon mu naught E cross B. Now this is the differential form. Let's find the differential form of the Poynting theorem. Now what we got, dw by dt is equal to minus d by dt of um, that is the energy of electromagnetic waves, minus of this 1 upon mu naught E cross B is nothing but S dA. The work done on the charge will increase when the mechanical energy density increases. For W is equal to integration over the volume mechanics V. Now, this UM is the electromagnetic energy. Therefore, density is integration over volume UME dT. Now, UME will become what? Half of epsilon naught E square plus 1 upon mu naught B square. Therefore, d by dt of work done equation, integration of UM mechanical dt B tau is equal to d by dt of integration over volume u e d tau minus of integration over closed surface s dA. Now if we take this term to left, we will have d by dt over the volume d tau mechanical energy plus electromagnetic energy, which is equal to minus of minus integration over closed surface s dot dA. Now, if we replace this by divergence theorem, integration over volume del dot s, so and cut out the volume integration on both the sides, then we will have partial derivative. This we have taken d by dt full derivative inside the integration, so it's become partial derivative d by d by t. Therefore, d by t electromagnetic energy, sorry, mechanical energy plus electromagnetic energy, which is equal to minus del dot s. Newton's third law in electrodynamics. Now consider two identical charges Q and Q1 and Q2 moving along x and y axis direction with velocity v1 and v2 respectively. Let the speed of both the charges are equal, though the electromagnetic force between them wouldn't tend to drive their path away from the axis, but let us assume they have been put in the same track and forced to maintain their speed and direction. The electric force between them is repulsive, as you can see. F is repulsive, having same magnitude but opposite in direction. Similarly, if you look at the magnetic field B, this is also repulsive. One direction is like this, another direction is like this. But this is a magnetic field. What about the magnetic force? Magnetic force on the charge Q1 and Q2 exert on each other. The moving point charge does not constitute a steady current. It means you can't apply the Biot-Savart law in this case. Therefore, the direction of magnetic field B1 and B2 produced by Q1 at Q2 will be in opposite to the magnetic field produced by Q2 at Q1. But magnetic force produced by these two are not opposed to each other. And here the Newton's third law violates electrodynamics. In electrostatic and in magnetostatic, the third law holds. But in electrodynamics, it does not. Momentum conservation reset on cancellation of the internal force, which follows from the Newton's third law. Now, this momentum conservation is rescued in electrodynamics by recognizing the field themselves carry the momentum. Okay, as the amount of momentum lost by the particles in doing any work will be gained by the field in the form of energy. And as the energy momentum, that is field momentum, is added to mechanical momentum of the charge, will restore the conservation of the momentum law. And this is how the Newton's third law in electrodynamics will save. The wave equation in electrodynamics. In free space, there is no charge exists. Since there is no charge, there is no current exists. Therefore, charge density and current density get vanished. Therefore, Maxwell equation will reduce to del dot E equal to 0, del dot B equal to 0, del cross E is equal to minus delta by delta T of B, del cross B is equal to mu naught epsilon naught delta by delta T of E. Now we will find del cross E. Now del cross E, that means del cross this term is minus debba by debba t of B, minus debba by debba t of del cross of B. Now del cross E is actually by the vector analysis has gradient del dot E minus del dot E is equal to minus debba by debba t. Now del cross B is nothing but mu naught epsilon naught debba by debba t of E. We will substitute this value. As you know, this term del dot E from above equal to 0. So what remains? Minus of del dot E. Minus of E, this del dot is del square, and minus sign debba by debba t over here, debba by debba t over here will make a square. So mu naught epsilon naught debba by debba t square E. Minus get cancelled. We will result L square E is equal to mu naught epsilon naught debba square by debba t square E. Now let's find, this is the 9.4.1 equation. Now let's find del cross P. As we have done for the electric field, we will do for same for the magnetic field. And del cross B is equal to mu naught epsilon naught debba by debba t of del cross E. As we know, del cross is nothing but minus of debba by debba t of B, and del dot B is equal to 0. Therefore, del dot B minus del dot B is equal to minus mu naught epsilon naught debba square by debba t square B. This term gets 0 and this remains. And same way as we have for the electric field, we have for the magnetic field. The equation 9.4.1 and 9.4.2 are the two second order differential wave equation. Next topic, velocity of the electromagnetic wave. The general wave equation moving in any arbitrary direction in 3 dimensions is del square of function f with the position vector r in the time t is equal to 1 upon c square, the partial derivative second order of function f with respect to of a function of position vector r and the time t. Now here you can see is the velocity c. This is the propagation of the velocity of propagation of the wave. Now by comparing this equation 9.5 with the 9.4.2 or 9.4.1, what we conclude that 1 upon c square is nothing but mu naught epsilon naught. Now that means c is equal to 1 upon under root of mu naught epsilon naught. As we know that mu naught and epsilon naught both are constant quantity, that is mu naught is equal to 4 pi into 10 raised to minus 7 and epsilon naught is equal to 8.85 into 10 raised to minus 12. If we substitute these values in above equation, the result comes around c is equal to 2.9999 into 10 raised to 8 meters square. And this is the velocity of light wave. And this shows that the light waves are electromagnetic wave. Plane monochromatic magnetic wave. Different frequencies in visible range are corresponding to the different colors. Monochromatic means a wave with a single frequency. Now consider a monochromatic wave with the frequency V and the angular frequency omega. That means V is equal to omega by 2. Let wavelength to be lambda and the wave vector to be k, such that k is equal to 2 pi by lambda. Then the velocity of the wave will be c is equal to omega divided by k. Plane means that wave propagating in one direction, that is, let's suppose this is in the z direction, having no x and y component. And let vector E, that is electric vector, and the magnetic vector B are electric and magnetic field presenting an electromagnetic wave traveling in a positive direction of the z. Then these are the like conjugates. Okay. The electric field is equal to z, as it's moving in a z direction, z t, and this is the amplitude e raised to exponential term e raised to I kz minus omega t. In a similar way, we will have for magnetic field. Now these E0 and D0 are complex amplitude. Electric field component can be written as for x component, for y component, and for z component, as we writing for the same for magnetic field components also. Now, electromagnetic waves are transverse waves. This is the main one of the topic, whether they are longitudinal waves or transverse waves. Now, wave which has a vibration perpendicular to the direction of propagation, these are called transverse waves. And from the Maxwell equation, we have del dot E equal to 0. That means deba x of Ex, deba y of Vy, deba z of Ez is equal to 0. Now this Ex and Ey is 0, since we have already said that complex conjugate E electric field E vector does not have any x or y dependency. That means this shows that only these terms deba z of Ez is equal to 0, which means Ez does not contain x explicitly. You cannot open electric field in z direction. But assuming that we have a z direction, for Ez we have this equation. In order that Ez does not contain explicitly, E0 z, that is amplitude, must be 0. Therefore, Ez will become to 0 because this exponential term e raised to I kz minus omega t cannot be 0. So what remains? Only the amplitude, and that makes it 0. In similar manner, if we say for the magnetic field, for equation del dot B we have same way as for electric field, and we will find the nearly same result. And this shows that this Bz equal to 0 and Ez equal to 0 prove that z component of Ex, Ez and Bz are 0. Hence, there is no longitudinal component of Ez or Bz, only perpendicular to the direction of propagation. Now, second, what we have to see whether these are perpendicular to each other but in phase with Bz. Now consider the x component of the Faraday laws, del cross E. Let's suppose only the x component. Therefore, deba y of Ez minus deba y Ey of deba z minus deba t of Bx. As we have find before that Ez equal to 0, that means only this term remains. Deba z of Ey is equal to deba t of Bx. Now, by definition, what we have of Ey, as we have defined before in above, this definition, Eyz is equal to E0y e raised to I kz minus omega t. And Bx similar way above, Bx Bz is equal to Bx 0 x e raised to I kz. Putting the above in above equation and taking their partial derivative with respectively, and we will get the result as I times k e0y e raised to I kz minus omega t minus omega b ox e raised to I kz minus omega t. If we cancel exponential term on the both side, we will get, and imaginary term I, we will get k e0y is equal to minus of omega b0x. Similarly, if we see for the y component, we will get result as k of O0 x is equal to omega bo0 y. Here you can see only the minus sign is different. Otherwise, the similarity is same. And taking the consideration of above equation, these two, and combining into the single vector equation, will result into that vector B, which is the amplitude of magnetic field, is equal to k by omega vector k cross product with the Ez. Now we know that k by omega is nothing but omega by 1 upon c. Then c is equal to omega by k. Therefore we get b is equal to k by 1 by c k z direction cross product with the electric field amplitude. The same relation holds for E as for B. And this concludes that E and B both are perpendicular to each other, and they are perpendicular also to the direction of propagation of the wave. As you can see from the figure, these both are perpendicular to each other, even perpendicular to the direction of propagation. Waves are traveling in any arbitrary direction, and since we have before in two cases we consider that wave is traveling in z direction. Let's suppose wave is not traveling in z direction. What will happen? Let k be the propagation vector of the wave, or simply called wave vector, pointing in the direction of the wave propagation. The direction of electric field E is perpendicular to the direction of k, and it is denoted by n cap, unit vector n cap. The direction of electric field E also direction of polarization of the electromagnetic wave. Therefore, unit vector n cap is called polarization vector. Then the equation of electric field and the magnetic field is shown as electric field, as we have defined before, is R E is equal to complex conjugate is 0 e raised to I k dot r vector r minus omega t in the direction of n cap. And B, from the above equation, what we say, B is equal to C 1 upon C k cross E. So we will get over here B is equal to 1 upon C E का equation जो है E 0 e raised to I k dot r minus omega t n cap cross product with the k cap. Now, as you know, since n cap and k cap both are perpendicular, so n cap dot k cap is equal to 0. Considering the factor due to the complex nature of the amplitude, let phase factors to be a delta. Now, this main thing is that this shows that wave to be travel in any direction, and you will find that electric field vector is perpendicular to the propagation of the wave, and the magnetic field vector is also perpendicular to the propagation of wave, and these two field vectors are perpendicular to each other. Now consider the phase factor due to the complex nature of the amplitude. Let phase factor to be delta. Therefore, same equation of electric field, but we will add the phase factor in exponential terms as kr minus omega t plus space vector delta. Similar way, in the magnetic field we also add delta. Energy, momentum and Poynting vector of the electromagnetic wave in vacuum. Energy density. We have already discussed this in the same lecture that UME, electromagnetic energy, is equal to energy due to electric field plus energy due to the magnetic field. That is 1 by 2 epsilon naught E square, 1 by 2 mu naught E square. For monochromatic plane wave, B is equal to E by C. That means B square is equal to E square by C square. That means 1 upon C square, as we know, is nothing but mu naught epsilon naught. We will substitute that value over here. Therefore, B square is equal to mu naught epsilon naught E square. Now, EM we know is 1 by 2 mu naught B square. If we replace this B square with above mu naught epsilon naught E square, therefore EM will equal to mu naught get cancelled. 1 upon mu naught is equal to E square. And that shows that magnetic energy is equal to the electric energy. Above equation shows that electric and magnetic field contribution to electromagnetic density are equal in vacuum. That means these are equal. Therefore, we can write twice of E to E. That is 2 get cancelled, epsilon naught E square or 1 upon mu naught B square. Now, if we see the electromagnetic energy again is equal to epsilon naught E square is equal to epsilon naught E square cos of square. We will consider on a real term of equation of exponential kr minus omega t plus the phase factor delta. That the average is equal to average of cos theta also. And this average of cos theta is equal to half for one complete circle. Therefore, average energy is equal to 1 by 2 epsilon naught E square. Poynting vector. A Poynting vector is the energy flux density, or you can say energy crossing the unit area normally in the time. That is given as we have discussed, as is equal to 1 upon mu naught E cross B. In plane monochromatic wave, where we find that E and B are perpendicular to each other, S will be the in direction perpendicular to both of E and B. That means in the direction of wave propagation. Now, S equal to in magnitude E dot B divided by mu naught. Now, what we have already find in magnitude is equal to E by C. Then we will substitute over here. In place of B, E by C, we will get as equal to E square divided by C mu naught. And C mu naught, since EME is equal to epsilon naught E square. If we find replace this E square by EME by epsilon naught. And what really we know that is C, this term is nothing but 1 by epsilon naught mu naught is nothing but C square. We keep it, what we find that electromagnetic energy times C is nothing but your Poynting vector. And the direction, if you oppose, then it will be in the direction of Z. Since wave is traveling in a Z direction. Now, is as we have defined above is pointing in the direction of wave propagation. The average value of S vector will be the average value of energy, electromagnetic energy, and this average value is 1 upon 2 epsilon naught E square. We substitute in a Poynting vector equation, which is result into C times half of epsilon naught E square cube. Now, intensity of electromagnetic wave is defined as the average Poynting vector is average power per unit area transported by the electromagnetic wave. That is nothing but the Poynting vector. That is I intensity is equal to nothing but the Poynting vector S is equal to C times half of epsilon naught E square A. Next topic, momentum. Now, momentum. The electromagnetic field not only carry the energy but also carry the momentum. Consider a cylindrical area of a cross section A and the length of C times T. C is the velocity of the light. Having its axis parallel to the Z, and the Poynting vector is the energy crossing the unit area per unit time. Therefore, S equal to electric field E divided by unit area, that is A, per unit time, that is T. Now, electric field energy E. Let E be the energy in the time T. The momentum and energy are related to each other. How? They are directly related. E is equal to P times C. P is the momentum and C is the velocity of the wave. Therefore, we can write in place of E as EC divided by T. This is equal to AT divided by C times S. Now, if we multiply C above and below, what will we get? ACT divided by C square S. Now, this CT is the length of the cylinder. That means area into length. Area into length is the volume of the cylinder. Therefore, P is volume divided by C square S. Now, if we talk about the momentum density, we have already said that momentum density is equal to momentum divided by volume of that system. Therefore, it is S vector divided by C. The average value of momentum will be average value of S vector divided by C. That is intensity divided by C square. Now that is equal to 1 by 2 epsilon naught E square divided by C vector K in the direction of propagation of wave. And this is my bibliography for this PDF.